Excellent. We're live. Haha. Wonderful. Okay. As I said, we've been going through linear regression. I want to continue going through linear regression. Last class, I introduced the concept of re-expressing data. And we're going to be doing something with this information in a few minutes. I want to make sure everyone's kind of on the same page with this and kind of get set up correctly. If you need to use said notebooks to do the following example, please by all means do so. But you will also need a graphing calculator of some sort. So of course, if you need those Chromebooks, by all means, break out those Chromebooks. I just realized there's a block of wood there. That's awesome. Where'd that come from? Where? Is it actually a block of wood? Okay. We used to sell those at Michael's. Oh, you didn't? I never told you guys that. Did I ever tell you I worked at Michael's during the summers for like 5 years? No? Yeah, I worked the 5 a.m. shift. It's great. I stocked shelves, I built stuff, and I unloaded trucks. It's awesome. I did it up till a couple of years ago. But anyway, I digress. Arts and crafts are dumb. Anyway, no, they're really not. So here's what I want you to do. Here is a set of data. Now, I want to give you context to this, so I am going to read to you what the context is instead of putting it all up on the board. So if you have any body piercings, you probably know that the gauge of your jewelry, which is a measure of size, is a lower number for larger jewelry and a higher number for smaller jewelry. For example, if you wanted a nose ring, you might initially get a small gauge 16 piercing, and then over time, stretch it to a gauge 14, then a gauge 12, and so on. The table below shows some standard jewelry gauges and gives the approximate corresponding diameters in millimeters. The gauge itself has no units. Then they're basically saying, oh, you can't really see it, but that's okay. Let's try to find a model that will estimate the diameter of the jewelry from the given age or a given gauge. And then they go into more details. Ultimately, what you're going to find out is that when you try to find the linear model and you look at the residual graph, and yes, I would like you to look at the residual graph, you're going to find out that the residual graph is not appropriate. The residual graph should show a pattern. Thus, you are going to have to re-express the data. You are going to have to re-express the data. So you're going to have to go through the ladder of powers. Now, of course, over the course of the next few minutes, I'm going to allow you the time to enter in the data, to find the residual plot, to take a look at that on your own. And I am going to put up that ladder of powers. Now, ultimately, your goal is this. Your goal is this. Actually, it's twofold, I should say. Number one, you are to find the appropriate re-expressed equation based on whatever function you end up using from the ladder of powers. So you are going to be finding that re-expressed equation. Let me freeze this temporarily. And then I want to make sure I get the right number here. Then we are going to use that re-expressed equation, there it is, to find out what the diameter would be of a gauge 3. So we're going to, number one, find the equation. Unfreeze, there we go. And then use that equation to find the diameter of a gauge 3. So I just want to point something out. It's pretty funny to me. So when I look at myself, I see like shirt and tie and like, you know, the short, whatever. I seem very like, you know, kind of clean cut, kind of straightforward type person. And yes, my wife is as well. My wife is a very, you know, straightforward person. You look at her and you're like nothing out of the ordinary. And it turns out, and I didn't know this when I first met her, but when my wife was in high school, she is what would have been considered a punk rock ska girl. I don't know exactly what that means, but apparently my wife, as kindergarten, elementary teacher that she is, would go to like Warped Tour and dye her hair all sorts of colors, and she was actually working her way up the gauge chart to kind of gauge her ears. It was really weird. When I met her, I'm like, who are you? But it was awesome to find that stuff out. Anyway, there's no point to that. I just wanted to share that. Anyway, so get to work. Enter in that data into L1 and L2. Find me the right equation. Of course, I want you to write whatever you end up getting, write it down. And then ultimately, you're going to use that equation to find out what the diameter of a gauge 3. There we go. Don't forget, if you're using the graphing calculator on the computer and you've reopened it, you're going to have to turn your diagnostics on. anybody thinks they got close or think they got something that they would like me to see, I would like to see it. I do have the answer written down, but I would like to see what you got if and when you get there. Find the rest. Find me the equation. Find me the millimeter for gauge 3. Was that just the original L1 answer? Okay. The problem is though, the residual flash is the third pattern. That they just installed on my computer. Sorry, I just find that interesting. I don't know. I might use it in a little bit. Just because I want to try and be on the same page as you guys with trying to type these things out. Let me do that. Let me type this list in just for the sake of argument. Just trying to recap some of this with you guys while you're still kind of perusing this information. To make sure we're all on the same page, let me show you what the original scatter plot actually was and what it did. The original scatter plot, if you go second y equals, turn that thing on, it's on a thing, blah, 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 blah. Cool. I'm going to zoom 9 it. Oh, it's just time to get my y equals key. Get rid of that. There we go. Zoom 9 it. There's the original scatter plot. Now, if I were to run some diagnostics on this thing, let me turn that on first. Diagnostics on. There we go. And I were to run a linreg using that L1, L2, calculate, boom. It's the original information that they gave me. Which let me just double, yeah, and then, but something's not right. Because if I'm going to do this thing correctly, I want to make sure that I look at the residual plot. If I'm going to look at the residual plot, there's a clear pattern in my residual plot. And having that clear pattern is not helpful. I'm just double checking my calculator here. I feel like I mistyped something. Let me check something real quick. Hold on. I feel like I mistyped something. Did I mistype a data point? Oh, I'm missing a couple? Oh, no, you're totally right. I'm totally missing a couple. I don't know why I didn't do that. Let's do it again. All right, cool. 16, 18, 20, 1.2, 1, and 0.8. Cool. Rerun the regression. L1, L2. Yes, those are the numbers that I should have gotten. And then I'll zoom 9 it for the residual. There's the residual plot for the original. Now, the thing is, using the calculator to do this, because this is probably the first time that a lot of you guys are really going through this process of using the ladder of powers. It's the first time that a lot of you are going through this ladder of powers. It can be a bit cumbersome trying to, okay, what step do I type next into the calculator? But the more practice that you get with it, the more fluid and smooth that it's going to be transitioning from one step to the next. Now, just for the sake of argument, I want to just draw in my ladder of powers right here. Square, 1, 1/2, 0, which is actually a log, -1/2, -1. There's my ladder of powers. I'm going to have to re-express this data. Anyone have an answer for me before I kind of share this information? Look at all them scared looks. It's nice. Anyway, I'm going to have to re-express my data. And in re-expressing my data, I'm going to start at the top of the ladder. Right now, everything is just with that power of 1, no changes. But if I go into my list, I can do this. Now, notice where I'm highlighted. By the way, question, is this the interface that you guys have on the computers? Very similar, or is it slightly different? Okay, just making sure. Okay, because I'm not as familiar with this interface, but we'll see what happens. I don't know. So I am going to have to first square everything. So I'm going to go second L2 squared. There we go. Enter that. There's all the squared data points. Nice. Let me rerun the regression. Oh, come here, you. There we go. Rerun the regression. But this time, I have to type in L3 in order to rerun that regression because I'm using the re-expressed data points in L3. Calculate, boom, it reran the regression. Now, here's where you can save yourself some time. Look what's in plot 1. I'm not going to change plot 1. So in reality, all I got to do is zoom 9 it. This is the residual plot for when I squared everything. Let's do it again. I mean, clearly there's still a pattern. I can't use the square. So I'm going to go back into my list. I am going to re-express the data. Notice I went up to L3. And I'm going to go down the ladder of powers. Boom, I just square rooted everything. I'm going to rerun the regression. By the way, do you know how to bring up stuff that you just recently calculated? Do you know what I just did to get that? I hit second enter. Second enter. I literally clicked that with the mouse. Second enter, and it brought that right back up. Boom! It just reran the regression. Zoom 9. There's the new residual plot. But this residual plot, again, is not right. It has a pattern. So I'm going to go back into my list. I'm going to go back up to L3. I'm going to go log of L2 because the next power is 0, which you wouldn't raise everything to the 0 power. You would literally do the log of that. Enter. It recalculates everything using logs. I'm going to rerun the regression. Now watch this. I'm going to hit second enter. Second enter. And it just brings it right back, which is nice. Boom. It just reran the regression. It's very repetitive. It's very repetitive as long as you kind of get the flow to it. Zoom 9. Ha-ha! Now we have a residual graph that appears to be scattered. Yes. Now at this point, you could be like, got it, I'm going to go with log. If you wanted to, you could go a little bit farther. Stat, edit, up to here, 1 divided by the square root of L2. And get rid of that. There we go. Yeah, there we go. Because it would be negative 1/2. You're going to find out in a moment that it didn't actually work. Because when I rerun the regression with the square root, I get a pattern again. Or with 1 divided by the square root, I clearly get a pattern. Or more of a semblance of a pattern. So I'm going to go back to log. I went too far on the ladder of powers. Boom. Zoom 9. There's my log. So what I have is this. Since logarithms appear to give me the best residual plot, then log of y hat is equal to negative 0.0504, rounds up, x plus 0.9003. That would be the appropriate model. That would be the appropriate prediction model. I had to re-express that data using logarithms. Then using that equation, the question that I then said was, okay, let's try to figure out what the diameter is for a gauge 3. Now, keep in mind, this is nothing more than a prediction. This is a prediction. That's all we can really do with that. So, gauge 3, I'm going to go back to my calculator. I'm going to do a gauge 3 on here. So, let's see. Negative, blast you. All right, I wrote it down over here. Can I not get in? Oh, if I keep typing negative there, I'd have to go here then. Negative. There we go. Negative 0.0504 times. Is that actually times? Hold on. 0.0504 times. Oh, that's scary. It looks like a spider. Anyway, times 3 plus 0.9003. Are you kidding me? Does it do that for you guys when you hit delete? Does it? That is frustrating, right? That's a design flaw right there. Sucks to be this calculator. Boom. Now keep in mind, that's not our answer. That is not our answer. That is what happens when you plug 3 into this equation. This is really log of y hat equals 0.7491. As we talked about last class, you need to get that y hat by itself. You want to get rid of the logarithm. It's a base 10. You take 10 to the power of both sides. My microphone. 10, there we go, to the power of, I'm just going to type in the answer there. There we go. Chapow! There it is. That's actually what it is. That is the predicted diameter measured in millimeters, of course. It is a predicted diameter measured in millimeters using the prediction equation that we re-expressed using logarithms because, well, it gave us the best scattered residual plot. I love problems like that. You're going to see. Now, as I said at the beginning of class, I don't plan on assessing linear regression until near the end of next week. So my intention for the next couple of class periods is to review, to kind of drive the point home with what we've been doing. So here's what I want to do with the remainder of the time that we have. I want to go back to those multiple choice questions. I had an idea as to how to actually do groups in a safe way, but I'm still working out the details. So keep in mind, whenever we do the next time we do multiple choice questions after today, I do have an idea for groups, but I'm still working out some of the details and flaws. So just keep that in mind. But in the meantime, what I'm going to need, you can close up them Chromebooks, keep those notebooks out, and pull out that white erase board from under your desk. Because I want to do some multiple choice questions. Yeah. Still from there. Okay. Now, there were some problems that I decided to skip over last time because they were going to, what's the word I'm looking for? Take a little bit too long to get into, and we only had a little bit of time left. But I really want you to see what these questions are. These questions, these multiple choice questions are going to be the caliber of question that you would be faced with on the AP test. The caliber of question that you'd be faced with. It's not just going to be something very straightforward and simple of like, hey, what's the equation for a linear model? Like, no, that's baby stuff. You are going to be faced with some grown-up statistics questions like this. Zoom back out a little bit. I'm going to read this one, so don't worry. A study is conducted relating AP Stat exam scores to the total number of study hours for the AP Stat class put in by students during the academic year, and the correlation is found to be 0.6. Which of the following are true statements? Now, again, just to clarify, they equated two variables. One variable was the total number of study hours, the total number of study hours and the AP exam scores, comparing the two, and they found a correlation to be 0.6. Again, correlation is your R value, your correlation coefficient. Which of the following is true? Now, I'm going to read all three, and then I'm going to give you a moment to kind of pick one. Number one, on the average, a 40% increase in study time results in a 24% increase in exam score. All right. Number 2, 60% of a student's exam score can be explained by the number of study hours. Okay. Number 3, higher exam scores tend to be associated with higher number of study hours. All right, cool. Now, I want to point something out to you. You know how usually when you do a multiple choice thing, and then the last one's like none of the above? This one is not none of the above. This does not say none of the above. What it says is none of the above gives a complete set of true responses. So it's basically saying like, hey, one of these or two of these could be true, but it's not listed in one of the choices. So just to be very careful, because they will try to mess you up with that. Give it a shot. While you guys are still thinking about it, somebody tell me, how long is the multiple choice section of the AP Stat test? Do you know? 90 minutes. How many questions do they give you? 40. Which means on average, they expect 2 minutes, 15 seconds per question. It doesn't seem like a lot of time. Some questions are going to take you like 5 minutes. Some questions are going to take you 30 seconds. My job is to get you prepared for that. We're preparing for battle. We're preparing for war. I don't want any casualties. I want to win. Winning is getting every single person to pass. That is my goal. Hold up your answers. I want to see them. Pick one. Hold them up. Hold them up over the thing so I can see it. Let's see. Wait, what's it say above your letter? Art? Oh, it's the letter R. I thought you were doing something. Okay, cool. Interesting. A bunch of different answers. Cool. Okay. All right. Let's see. Let me work in reverse because this is going to be easier if I work in reverse. Number 3, higher exam scores tend to be associated with higher number of study hours. Yeah, that's kind of fluffy language. That's true. That's a true statement right there. Higher exam scores tend to be associated. They're not saying they are. They're not saying, hey, study more, you'll score better. They're not saying that, but they're saying that, hey, on the average, they tend to be associated. Yeah. Number 2, working backwards. 60% of a student's exam scores can be explained by the number of study hours. That kind of sounds like what? That statement, number 2, sounds like what concept that we've covered? Sounds very similar to it, but not exact. Not exactly. What did we call the coefficient of determination? R squared. It sounds like R squared. It may not be exactly R squared, but it sounds like R squared. But R squared wouldn't be 60% anyway. R squared would not be 60% anyway. You want to get R squared, you got to square that sucker. Because that's R. So that's clearly not true. All right. So hold on. Process of elimination. Being the good student that you are. It can't be this one. It can't be this one. It can't be this one. Now you got a 50-50 shot. The first one. On the average, a 40% increase in study time results in a 24% increase in exam score. Wait, what? 40% increase in study time results in a 24% increase in exam score. Let me do something here. See where they got these numbers from. Yep, that's where they got those numbers from. They got those numbers from, 0.24 divided by 0.40 equals 0.6. That's where they got those numbers from. I've never once expressed R really as that. On the average, a 40% increase in study time results in a 24% increase in exam score. Well, when it comes to expressing slope, usually we do something along those lines where we're talking about, well, for every increase in the X value, there is a predicted increase in the Y value. But I've never seen it done directly with R. Let's see what the back of the card says. Oh, yeah. Oh, no, it fell. Answer Z. The slope has the same sign, but generally not the same sign as the correlation. The coefficient of determination giving the proportion of the Y variance that is predictable from a knowledge of X is not equal to R squared, not R. A positive correlation indicates the higher values of X tend to be associated with higher values of Y. Yeah. That first statement, I think what that first statement was trying to do was they were trying to express some kind of a interpretation of slope. They were trying to express some kind of interpretation of slope. But the slope is not exactly 0.6. The slope is not exactly 0.6. That's not how you calculate slope. Slope would be R times the standard deviation of Y over standard deviation of X. Weirdness. Let's see what else we can do. Ooh, there's a good one. Let's go over here. Does it bug anyone that I leave those marks on the board? Never mind. I won't do it. I have one problem with this question, and I'll change it once I get up there. Let me start reading them. Data on ages and years and price in hundreds of dollars for 10 cars of a specific model result in the regression. Now it's fixed. Price equals 250 minus 30 times age. Given that 64% of the variation in price is explainable by the variation in age, what is the value of the correlation coefficient? This one, theoretically, should take you no more than a minute. It really does bug me that they didn't put the hat on the word price. They really should. Because it's based on 10 specific cars. It's based on a sample. And I'm sorry. I need to stop yelling at the card. I'm going to be asking for an answer in the next 10 seconds. Make sure you write one down. All right, hold them up. Let me see them. Hold them up. Interesting. There we go. Okay. A little higher. There we go. Lots of A's, lots of C's, and a B. Lots of A's and C's. Oh, I see why you did that. Interesting. It's neither A or C. Given that 64% of the variation in price is explainable by variation in age, tell me, what is that describing? It's describing R squared. They didn't ask for R squared. R squared is 64, or 0.64, I should say. But that's not what R is. R is definitely not 0.64. R squared is 0.64. Thus, you got to take a square root. But here's the thing. What have you been taught in the past about like introducing square roots to problems? When you introduce a square root, it could be either the positive answer or the negative answer. Well, R will have the same sign as the slope of the linear model. The slope of the linear model is negative 30. Thus, R, when you take the square root, negative 0.8. Yeah! I love problems like that. This is the type of problem where people will read it and they'll be like, oh, got it, and they'll mark it and then move on. And they'll never think about it again for the remainder of the multiple choice section. But then it's like, oh, that one tiny little thing could have saved you. That one tiny little thing could have saved you. Let me flip the card over. Not only for confirmation, but just to see the explanation that they gave there. Yep, we're given R squared equals 0.64. We need the slope of the regression line is negative. The correlation has the same sign in the slope. So we have R equal to negative square root of 0.64. Solid. Excellent. Again, these multiple choice questions are designed to mess you up. Here's the thing. 40 multiple choice question. 40 multiple choice questions. If you are able to get 20 or more correct, you have a very good shot of passing the AP test. Let me repeat that statement. Out of 40 multiple choice questions, if you get 20 or more correct, you have a very good chance of passing the AP test. The assumption being that the remainder of whatever score you needed would have been filled in by the free response. But I'm just saying, I've seen people basically blow off the free response and pass solely based on their multiple choice skills. It's ridiculous. Why did you just blow off the free response? You could have done so much better. I'm just saying, you need to have that complete package. Multiple choice and free response. Don't like that. Ooh. There we go. Consider the following 3 scatter plots. Which of the following is a true statement about the correlations for the 3 scatter plots? All right, write them down. Pick an answer. Remember, we're not leaving any blank. You got to make a choice. You got to give yourself a shot. Hold them up. Let me see them. Let me see them. Hold them up high. Lots of. Okay. Mostly B's and E's. I got some D's mixed in, a C or two, but I got mostly B's and E's. Interesting. All right, which of the following is a true statement about the correlations of the 3 scatter plots? Well, first of all, correlation is your R value. R value is the strength of the linear association. Now, clearly, this one is not exactly linear, but that one has a pretty strong correlation. That has a pretty strong linear factor to it. And I've showed you this in the past. I have showed you a scatter plot that clearly is curved. But when we calculate the correlation, it ends up being pretty darn strong. None of them are 0. Well, that's not exactly true, because this one definitely looks like a correlation of 0. It looks like the negative correlation and the positive correlation end up canceling each other out. None of them are 0. That one's gone. Definitely one is negative. The first one's definitely negative. I would say that. This one definitely seems to be 0 to me. But that last one kind of throws me off. It's like if I were to draw a line through it, like a line of best fit, it's almost like it would just be like a horizontal line or some junk like that. It appears to me like the last one also has a correlation of 0. I think it's E. Which, let me specify the difference between D and E. D, it says the other one is -1. Oh, that's definitely not -1. -1 would be a perfect straight line. Close to -1, sure. I think it's E. Yeah, it's E. All 3 scatter plots show a very strong non-linear pattern. However, the correlation measures the strength of only a linear association. Thus, R is close to -1 for the first one and 0 for the other 2. Love that kind of stuff. Multiple choice questions. They will mess you up every single time because they are designing these questions in such a way to specifically mess you up. That's what they like to do. I don't like that one. I'll come back to that one another time. Ooh. This is a fun one. Hold on. If every man married a woman who was exactly 3 years younger than he, by the way, it sounds like a riddle when they word it like that, what would the correlation between the ages of married and men, I'm sorry, let me read that again. What would be the correlation between the ages of married men and women? I feel like if they really wanted to go all in, they would have rhymed that thing. There we go. All right. Hold them up. Let me see them. Hold them up high. Hold them up high. Okay. Mostly D's and E's. It's a good mixture of D's and E's across the board. Interesting. D's and E's. Nearly 1 and an exactly 1. Now, here's the interesting thing. If every man married a woman who was exactly 3 years younger than he, what's the typical age to get married for a guy? I don't know. Dan? 28, sure. If the guy's 28, can we agree the woman's got to be 25 according to this? According to this, exactly 3 years younger than he. Now, mind you, they said every 30-year-old marry a 27-year-old. A 33-year-old would marry a 30-year-old. A 21-year-old would marry an 18-year-old. The man would be, the woman would be exactly 3 years younger than he. And if I were to plot all of that junk out, 10, 20, 30, whatever. Okay. This is a terrible scatter plot. I don't know what I'm doing here. It'd be like 33 and 30. It'd be 30 and 27. There we go. It would be 21 and 18. It'd be whatever. You can see it right there. It's going to be exactly 1. It's going to be exactly 1. That's what the back of the card says. On the scatter plot, the points would lie in a perfectly straight line. So if they lie in a perfectly straight line, which doesn't usually happen with scatter plots, but in this particular instance, it totally did. They like to fool you. They like to trick you. They basically say, here's a multiple choice question, and while you're reading it, they push you over. That's what they do when they create multiple choice questions. The people who create these questions hate you. They want you to fall over. They've designed, oh no, the whole thing broke. That's fixed. They designed this whole test to make sure that most people don't really do that well. And then in the end, they take all of your scores, line them up from least to greatest, and then basically are like, okay, top 60% pass. Lower 40% don't. That's what they do. That is exactly what they do. I want to do one more question. I got like 2 minutes. Here we go. Last question of the day. Suppose the correlation between two variables is r equals 0.28. What will the new correlation be if 0.17 is added to all the values of the x variable, every value of the y variable is doubled, and the two variables are interchanged? I'm going to give you 30 seconds. 30 seconds to get this answer. Oh, hold them up. Let me see it. Hold them up high. Hold them up high. Hold them up high. Hold them up high. He's holding it backwards. I couldn't see it. There he is. Okay. All right, cool. Would it surprise you if it didn't change? It didn't change at all. These are in our notes. The correlation is not changed by adding the same number to every value or by multiplying every value, as long as it's a positive number that you are multiplying by. And if you interchange x and y, the correlation still does not change. Oh, I love it. They really love to mess with you. I'm going to finish grading those assessments hopefully today and give you the feedback that you so desperately crave from me. And then we'll talk again on Tuesday. All right, there's the bell. Goodbye, everyone.